So dear students, in this video I'll be talking about binary number system, and I'll be talking about the conversion of decimal system into binary number system. So what's a binary system basically? It's a system, it's a number system basically, which has only two digits. In terms of zeros and ones. And this number system is called as binary number system. Now, in decimal numbers, we have 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So the total number of digits used in decimal system is equal to 10. And the total number of digits that are used in this system, these digits, we call them base. Or we also call them radix. So a decimal system has a base or a radix of 10. Because their number is 10. And in decimal system, the number is expressed in terms of the place values. Now, for example, if I take an example of say 8,765. So this is 8,765. So I can write down 8,000 plus 700 plus 60 plus 5. I can also write it like 8 times 10 to the power of 3 plus 7 times 10 to the power of 2 plus 6 times 10 to the power of 1 plus 5 times 10 to the power of 0. The base of this system is 10. So what we see here the digit 5 to the extreme right that we have here has a place value of, it has a place value of 10 to the power of 0. And this is known as least significant digit. LSD, least significant digit. And the digit 8 that we have here to the extreme left, you can see the first number that we have here has a place value of 3. So here the place value is 3. So it is 10 to the power of 3. And this is known as most significant digit. Most significant digit. MSD. So what we have LSD, the least significant digit, and we have MSD, the most significant digit. All right. So this one is the least significant digit, and this one is the most significant. So this was about the decimal system. And in binary system, now let's talk about the binary system. Binary system. Now, what binary system has? It has 2 digits, okay? It has digits in terms of 0 and 1. Therefore, the base, or what we call radix, of binary number system is equal to 2. And the binary system has also a place value. And this place value is a characteristic property of this binary system. The digit to the extreme right that we discussed in terms of decimal system has to have a value of 2 to the power of 0. And this digit is called as LSD, least significant digit. And the next digit that we will have to the LSD has the place value of 2 to the power of 1. And the next has 2 to the power of 2. And so on and so forth. Now, if I take an example of, say, for example, I'll choose a binary number, 1, 1, 1, and 1. Now, in binary system, how we can write it? We can write it 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. And we can calculate it. So this will be 2 twos are 4 twos are 8, 2 twos are 4 plus 2 and plus 1, and that's 8 plus 4 is 12 plus 2 is 14 plus 1 is 15. So the decimal equivalent of this binary number, so I should write 1, 1, 1 and 1. What is its decimal equivalent? The decimal equivalent of this binary number is 15. Now each digit in a binary system is known as bit. So 1 is a bit here, bit. And a group of bits, what it makes? The group of bits makes byte. And this byte may also be called as word. It may also be called as code. Now, if we take the example of this 1, 1, 1 and 1, it's a binary number. How many bits it has? It has 4 bits, 1, 2, 3 and 4. And this number as a whole is a byte. It's a byte. And this byte is made of how many bits? This byte is made of 4 bits. Now, let's talk about the conversion. Conversion of decimal number. So conversion of decimal numbers. Okay. Now, the very first approach that we will try to do here is, now what we should do, we should express the decimal number as the sum of ascending powers of 2, and then collect the powers or the coefficients of each term, and that shall convert our number. So let's take an example. What am I trying to tell here? Suppose 6 is a decimal number, so it has a base of 10. Now we can write down this 6 as 4 plus 2 to the base 10. Now I can write down 1 times 2 to the power of 4 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. Now I have written down this in terms of the base equivalent to 2, the same number. Now the powers that we have, it should be 2 to the power of 2. That will give me 4. This should be 2 to the power of 1. That will give me 2. So now if we take the powers of these bases, now what are the powers? If we take the now what should we do here is, now the coefficient of this, okay, I'm doing it wrong. Now the coefficient of 2 to the power of 2 is what? It is 1. What is the coefficient of 2 to the power of 1? It is 1. What is the coefficient of 2 to the power of 0? It is 0. So the binary equivalent of 6, 10 is 1, 1 and 0. So what we have done is we have converted this decimal number into a binary number. So 6 to the base 10 is equivalent to 1, 1, 0 in binary system. That should be clear. Now the extreme right number of this, the extreme right digit of this number is 0, and this 0 is LSD. It is least significant digit. And the extreme left, with respect to me, this number 1 is most significant digit. Now this is one way of doing it. There is another way that we can do it. Now what we can do is we will take a number, we will divide the given decimal number by 2, and we will get the successive quotients by 2 till the quotient becomes 0. And the sequence of reminders that we will obtain during the divisions gives us the binary equivalent of the decimal number. And the most significant digit or the bit of the binary number so obtained is the least reminder, and the least significant digit is the first reminder that's obtained during the division. So this process we can use in terms of division. Now, if I take an example of, say, for example, let us take a binary. I want to have a binary equivalent of 2. 2 is a number, and I want its binary equivalent. So what am I going to do? I'll take 2. So 2 1s will give me 2. And what will be remainder here? The remainder here is 0, because it's exactly divisible. And 2 zeros will give me 0. So what will be remainder here? Remainder here will be 1. So in this case, this 0 is least significant digit, and this 1 is most significant digit. So I can say that 2 to the base 10 is equivalent to 1. Now you have to 1 0 to the base 2. Now let's take another example. Let's take another example of binary equivalent of. I want binary equivalent of say 12. So what should I do now? I should take 12. Okay, so 2 6 are 12. So what will be remainder here? It will be 0. So it is LSD. So 2 3s are 6. What will be remainder here? It will be 0. Okay, so this must be LSD. And 2 1s are 2. What will be the remainder here? 1. And then 2 zeros are. What will be the remainder here? 1. So this 1 is the most significant digit, and this 0 is the least significant digit. Now I can write down the binary equivalent of 12. Now 12 is with the base 10. This 12 with the base 10 is simply 1 1 0 0 binary. So this 1 1 0 0 is a binary equivalent of this number 12. And in this number, what we have, this 0 is least significant digit, and this 1 is most significant digit. Now, in the same way, I will take the binary equivalent of 13. Let us choose 13 now. Okay, if I have 13, so I will divide it by 2. 2 6 are 12, so remainder will be 1. So here 1 will be least significant digit. So 2 3s are 6, so remainder will be 0. 2 1s are 2, remainder will be 1. 2 zeros are 0, remainder will be 1. So what's going to be the binary equivalent of 13 here? So the binary equivalent of 13 here will be 1 1 0 1. So this is going to be the binary equivalent of 13. Now, we have the number in binary system, and we have to convert it into the decimal system. How should we do that? So now we will be talking about conversion from binary to decimal system. Now, what we have here, the least significant digit in the binary system is the coefficient of 2 with the power 0. Okay, this is the least significant digit here. As we move towards the left side of this LSD, the power of 2 goes on increasing. This thing can be, I'll take an example here. Say, for example, I have 1 0 0. So this 1 0 0 can be written as 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0. So what we are going to get here, this is 2 plus, this is 2 2s are 4, plus 0, plus 0, and this is going to equal to be 4. So here, what is this 1? This 1 is MSD. And what is this 0? This 0 is LSD. So the decimal equivalence of binary number, what is that? 1 0 0. It's a binary number, is 4 to the base 10. Now, if I take other examples to get the concept clear, and say, for example, I have 1 1 0. This 1 1 0 is 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 0 times 2 to the power of 0. So what am I going to get here? 4 plus 2 plus 0, that's equal to 6. Suppose I have 1, 1, 1. So it is 1 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. So this is going to be 4 plus 2 plus 1, and that's going to be 7. Suppose I have 1, 0, 1, 1. This is going to be 1 times 2 to the power of 3 plus 1 times 2 to the power of, it is 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. So how much am I going to get here? 2 2s are 4 2s are 8 plus 0 plus 2 plus 1. So this is going to be 11. Now similarly, I would like to take another binary number, say 1101. So this is going to be 1 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0. So this is going to be 2 2s are 4 2s are 8 plus 4 plus 0 plus 1, and this is going to be 13. So this is how we can obtain the decimal numbers from the binary numbers. So what we have learned from this video is that what is the basis of a decimal system, what is the basis of a binary system, and what are the different ways by virtue of which we can transform a number from decimal system to binary system, and from binary system to decimal system. Now, when we talk about gates, the question arises in our mind that what is a gate? And we should be able to write down the Boolean expression for this gate, and we should be able to write down the circuit diagram of this gate. Now, this OR gate. Before talking about the OR gate, I think better is to have some idea about gate in general now. A logic gate basically is a device which is used to perform some logical operations. So we have logic gate, and we make use of logical gates to have some logical operations in one or more logical inputs, and produce some single output, having some inputs and having a single output. So these logic gates are made electronically using diodes and transistors that are operated as electronic switches. So we have diodes and transistors, and they are used generally in the form of electronic switches. So these logic gates are basically the building blocks of any electronic circuit. So these are the building blocks of any electronic circuit. And primarily there are three kinds of logic gates: OR gate, AND gate, and NOR gate. And then all the gates can be developed from these basic gates. And there are gates known as NAND gates, NOR gates, and these NAND and NOR gates are also commonly used as logic gates, which are in fact combination of these OR and NOT gates. So what we have here is we will talk about the very first fundamental logic gate, which is called as OR gate. And for this OR gate, we have the relation that we talked about, the Boolean expression. So the relation between the output and the inputs is given by the Boolean expression. So Y is A or B. Now, output Y is available if any of the inputs are present in this case. So output will be 0 only if all the inputs, here in my case is A and B, if both the inputs are equal to 0. In that case, the output is going to be 0. And let's go with the logic symbol of this OR gate is something like this. So you have an input A, you have an input B, and you have a single output Y. And you have a single output now. The inputs can be more than 2 as well. So the point is, if you have any of the inputs which is on, you will always get an on output. And to have off output, to have zero logic, to have zero in the output, all the inputs must be equal to zero, must be in the state of off. Now let's go with the circuit of, let's draw the circuit diagram of the OR gate and then understand its operation. So let me go with that. Suppose what we have here is we have a PN junction. Say I will call this D1, and we have another PN junction, and I'll call this D2. And here we have input B. Here we have A, and let me call this 1, and let me call this 0, and I have a battery, say, of 5 volts, and here we have a resistor, and here I will obtain the output Y. Now what I have is this OR gate that I have drawn here, the circuit diagram of it, and it's prepared with the help of these two diodes, and these diodes are connected in such a way that their N regions, you can see that they are connected at a common point. It's connected at a common point in the given diagram here, and the input applied to A or B can either be logic 1 or it can be logic 0. And these diodes are assumed to be ideal diodes. Now, what ideal means here is that they have zero. These are zero resistance diodes. I mean, when A is connected to the positive terminal of the battery, then A is going to be 1, and 1 means high voltage. 1 means high. And when it is connected to the ground, when this A is connected to the ground, what happens? Then this A is acting as low voltage. So A gives us a logic of 0. So it gives us the output low. And if the diode D2 that we have is connected to the positive terminal of the battery, then B will be equal to 1 for positive terminal of the battery, so it means you'll get high, and B will be similarly equal to 0, implies that it is connected to the grounded terminal of the battery. So these are the basic logics that we can put here in this diagram. Now let us generate a case for it, and what we have here is, okay, now if I say when A is equal to 0 and B is equal to 0, that means both D1 and D2, both diodes in this case are reverse biased. So both will be grounded. So both of them will be reverse biased. In this case, none of the diodes, D1 and D2, they will not conduct. Hence, the output is going to be 0. So for A equal to 0, B equal to 0, my Y, which is output, this output is going to be 0. Now let's go with the next thing. What's over here? Now when A is equal to, suppose I go with A is equal to 0 and B is equal to 1. Now what does that mean? Now in this case, what's going to happen is that this D2 is forward biased and D1 is reverse biased. So D2 conducts, and the whole input voltage, which in our case is 5 volts, this whole voltage appears at the output diode, D2. This whole voltage, that we are talking about here, this input voltage that's of the order of 5 volts, it appears as the output of this D2, and which is ideal one. That is, no voltage drop takes place. The high voltage of 5 volts is represented by 1. So the output in this case will be equal to 1. So output in this case will be equal to 1. Now if I take A equal to 1 and B equal to 0. Now in this case what's going to happen is the diode 1 is forward biased and diode 2, which is D2, is reverse biased. So D1 conducts. The whole input voltage, which is of 5 volts, appears at the output of this D1, which is ideal one. So the high voltage means we get nearly 5 volts. And this is represented by the symbol of 1. So the output in this case is going to be 1. And finally, when I take both A equal to 1 and B equal to 1. Now what's going to happen in this case? In this case, both the diodes, D1 and D2, they are both forward biased, and hence both the diodes will conduct. The output voltages of the two diodes that we have obtained across R, they are in parallel. And if they are in parallel, so the net voltage that we will obtain here is going to be only 5 volts. Now this 5 volt is a representative of 1. So what's going to be the output in this case? So Y is going to be equal to 1. So these facts that we have obtained over here, we can tabulate these facts in a simple table. And what we have in case of OR gate is we have input and we have output. So here we have output and here we have inputs. So we have inputs A and B as inputs, and here we have Y as output. So for 0, 0, the output is 0. For 0, 1, the output is 1. For 1, 0, the output is 1. For 1, 1, the output is 1. Right? So this is how we can understand the working of an OR gate, how the output of this OR gate is obtained. Now, if we try to take some concept kind of thing, like suppose what in this case I will represent it by some discrete energy states like this. Let me take it something like this. Okay, then corresponding to this, okay, I have something like this. Okay, let me go like this, and then come back, then go like this, then go up and come back and go on and go on. Now this is my A and this is my B. Now this will be my reference as, say, T1, and this will be my another reference as T2, and then there will be another reference as T3, then there will be another T4, and then there will be another, and that will be T5, and then there will be another, and that's going to be T6. Now what we have here is we have low, then high, then low, then high, then low, and then high, and then low. This is how we can understand it. Now B, we start with low, then we have high, then we have high, then we have low, then we have high, then we have low, and then we have low. Now let us try to evaluate the output of this kind of thing. So how would the output look like in this case? So Y, if I go like this, so Y, so in this case, so here A0, B0, so I'm going to have the same thing here. Okay, then I will have something like this. Okay, and to the end, and then it will come down. Then now what I have is I have high for this situation. All right. So for this one is high, this one is low, so again I have high situation here. Now this one is high, this one is low, again I have high situation here. Now this one is low, this one is high, again I have high situation here. So this one is high, this one is low, again I'm going to have the high situation. Now both are low, so the output that I have here is low. So this is my T1, T2, T3, T4, T5, and T6. So what we can say here is that for T is less than T1, A is 0 and B is 0. That implies Y is 0. So that's given by this line. And then for another interval t1 uh, and t1 to t2, what we have? What we have is a is equal to 0 and b is equal to 1. Therefore, y is equal to 1. Then from t2 to t3, what we have between t2 and t3, we can see that a is 0 here and b is 1. So this implies y is equal to 1. And similarly, if I see between t3 to t4, then a is equal to 1 and b is equal to 0, so y is equal to 1. So this is how we can understand the digital output when we have two digital operations taking place, and how we can state out the OR operation when two inputs are given to an OR gate, and what is the output of that OR gate. So what is clear out here is that in case of OR gate, if we have either any of the inputs available, we will always get an output. Now, what is AND gate? And let's talk about AND gate. Now, this AND gate, it can have two or more than two inputs with one output, such that the output is available only when all the inputs are available. So this is the necessary condition for this AND gate. And then what we would like to do is that we would like to write down the Boolean expression for this this AND gate. So Boolean expression. So what should it look like? So it is y is a and b. So y is the output and a and b, they are the inputs to the AND gate. And we can read it as y equals a and b. Now, the logic symbol of AND gate is something like this. Okay, you can have two inputs or more than two inputs, but you will have only one output. So let us assume this is A, this is B, and this is Y. Now, let's try to draw the circuit diagram for the AND gate realization. We want to realize this gate. Now, what we have in this case is we have two PN junctions, and let's see. Okay. All right, so this is my point A, this is my point B. I'll call this as D1, this is D2, and a resistor R and supply of 5 volts and the ground of this, and then take other points. Grounded. So this is my B, this is my, I'll call this B1, and I may call this, say, say this is Y dash here, and here we will have Y. Now, this is a circuit realization of AND gate, and this AND gate consists of two PN junction diodes D1 and D2. They are connected in such a way that their P regions are connected to a common point, and that's clear from the diagram. And when A or B they are equal to 1, it means that A or B is connected to the positive terminal of the battery. And if A or B is 0, it means that the input A or B is connected to the negative terminal of the battery. Now, we can realize it in a way. Suppose when A is equal to 0 and B is equal to 0. Now, in this case, what we have, terminal A and terminal B, both are actually grounded. Because they are connected to the ground terminal of this battery B1 that we have. So what we have in this case, both the diodes are forward biased through the battery B1, and hence they conduct. And conduction of diodes in forward bias means full voltage in the output of the battery B2. And there will be a drop, B2 will drop in resistor R, and Y dash will be grounded. So what it means here is that through conducting diodes and grounded terminals of the battery B2, what we have is this is my B2, and I'll call this as B1. So when we have the grounded terminal of B2 and we have conducting diodes D1 and D2. So in this case, what's happening is that Y that we have is equal to 0. And now when A is equal to 0 and B is equal to 1. Now in this case, what's going to happen is D1 is forward biased and D2 is simply reverse biased. So D1 will conduct. As such, the output voltage is 0. That is, the output the output Y that will have will be equal to 0 because of the reasons that we gave in the previous case. All right, so what's going to happen here? This implies Y is going to be 0. And then there can be another important case, A is 1 and B is 0. Now what will happen in this case? In this case, diode D1 is reverse biased and D2 is forward biased. So diode D2 conducts. As such, the output voltage is again 0. That is, Y is equal to 0. And we have already explained that thing in the very first case when A is equal to 0 and B is equal to 0. And in that case, we have equally explained that both the diodes are forward biased through the battery B1, and hence they conduct. And when they conduct, the conduction of diodes D1 and D2 in the forward bias means full 5 volt of the battery B2. This battery will be complete, it will drop, its voltage will drop in the resistor R, and Y dash will be grounded. And hence through the conducting of the diodes and the grounding terminals of the battery B2 that we have, the output would be 0. So the same reasons goes with the case 2 and with the case 3. And finally, what we have, if A is equal to 1 and B is equal to 1. So now it's clear that both the diodes in this case are reverse biased. So they do not conduct. So no current will flow through the resistor R. And potential of the battery, which is 5 volt, will appear at Y dash. And this output of 5 volts will give us Y is equal to 1. So we can generate a table for it, and what we will have is we have A, we have B, and we have output Y. So this is A, this is B, and what we have 0, 0, I have 0, 0, 1, I have 0, 1, 0, I have 0, 1, 1, I have 1. Okay, now let's have some conceptual understanding of this AND gate. What would I like to do is I would like to visualize it in a shape of output signals that's obtained in a waveform from AND gate. So we go like this. Now let me call this A, and then what I have, this is my B, and what should be the outcome? So let me draw the dots first. That would be the right thing. So this is going to be like this. This is going to be like this. It's going to be like this. This is going to be like this. Okay, and then this is going to be. Now let us look for the output in this case. So how would our output look like in this case? So we will have something like this. Then we will be gone like this, and let me call this as T1 and this as T2, and this as T3, and this as T4, and this as T5. Now, what we can realize here is that for the interval from T1 to T2, what we have from T1 to T2, what is A? A is 1. And from T1 to T2, what is B? B is 0. Okay, B is 0. So what is Y? What is Y from T1 to T2? This is 0. So Y is equal to 0. Okay, so this is point number 1. Now for the interval T2 and T3. So now for this interval T2 and T3, T2 and T3. So what we have for T2 and T3, what is A? A is again 1, A is high. Okay, what is B? B is again 1. So what's going to be Y? Y is going to be up. So Y is equal to 1. Okay, so for the interval T3 and T4, T3 and T4, here we have, okay, what is A here? A is 1. What is B here? B is simply 0. So what is Y here? Y is 0. So we have a line. So similarly, we can find out. We can find out the other parts of this interval. So this is giving us a clear logic, the logical understanding of an AND gate. And we have two inputs, and then we have an output of this form. Hence, the shape of this output is given by this part. So this is my Y. What is Y? Y is A and B for this particular input of A and input of B. So now what is a NOT gate? A NOT gate has only one input terminal, and it has one output terminal. And what NOT gate is basically, what is the outcome, what's the logical outcome of a NOT gate is that it has one input, and this input is inverted to only one output. So it is inverted. So if I have to write down the Boolean expression for NOT gate, so Y is going to be A bar, or we can also say Y is A dash. Now, how do we read it? Y is equal to negated A, or we call it A dash is the complement of A. So Y is equal to negated A, or Y is equal to, or A dash here is called a complement of A. So if I have to, what does it mean is that if A is equal to 0, then Y is certainly going to be 1. And if A is equal to 1, then Y is certainly going to be equal to 0. It means NOT gate simply inverts the input. And due to this reason, we call it as NOT gate. And it is also called as inverter. So let's draw the symbol of a NOT gate. This is the symbol of a NOT gate. It has a single input A. It has a single output B. Now, to realize this NOT gate, we would like to have a circuit. And a circuit in which we have a transistor. Okay, let us have an NPN transistor. And let me ground its emitter. And let me have the base resistor here. And this is my point A. And then from here, I have the output Y, and here I have the load resistance RL, and here I have a battery. So this should be negative, positive, negative, and positive. So let us ground it from here, and from here, okay, I will call this as terminal 1, the 5-volt battery, and here we have a ground, and from here I have a terminal that gives me terminal 0. Now, so this hole is enclosed in this symbol of the NOT gate. Now, Since the input to be inverted, we have to invert the input signal. So a transistor amplifier in common emitter configuration is used instead of a PN junction or a diode, because we understand that a transistor in a common emitter mode inverts the input signal. And this type of transistor configuration certainly changes the phase of the signal, or what it does, it introduces a phase inversion. So the NOT gate is used in digital circuit. Uh, uh, this is a compilation of the NOT gate that's here. Now, let's develop a case here. I mean, suppose when I say that A is equal to 0. So what does that mean? A is equal to 0. Now, when A is connected, this A is connected to the grounded terminal of the battery, the emitter base junction that we will have, okay, this emitter base junction will be reverse biased. Quite simple, and hence there is no collector current, and the transistor is in cutoff state. So there is no potential drop across the load resistance RL. Thus, the output voltage is equal to the voltage of the battery. And what is the voltage of the battery? That's 5 volts connected to the collector. Since the high voltage is represented by 1, so Y in this case is going to be 1. Now, the next case can be when A is equal to 1. So how can we realize it? Now, when this A is connected to a positive terminal of this 5-volt battery, what happens? Now, this emitter base junction that we have here, the emitter base junction is forward biased. Now, when it's forward biased, we have large collector current. And this large collector current flows through the load resistance. The transistor comes in saturation state here. So here it comes in cutoff state. But here, the transistor goes in saturation state, and the voltage drop across this load resistance is equal to the voltage of the battery that we have here. It's equal to the voltage of the battery. Now, that's connected, and what will be the output in this case? So this battery is drained through this resistor. So output here is Y is equal to 0. So if I have to make a truth table for this NOT gate, I will have a simple situation like this, where I have input A, and if I give, here I have output Y. If I give 0, I'll get 1. If I give 1, I'll get 0. Now let us try to realize this this NOT gate using a signal. Now let me draw something, say something like this. Go like this. Okay. Let's go like this. Now this is my A, and I will call this as T1. I will call this as T2. I will call this as T3. I will call this as T4, and I will call this as T5. Now, what would the output look in this case? Okay, the output would certainly have a situation like this. If I start from here, this is my Y now. Okay, so it will go like this. Okay, then it will go like this, then go like this. Yeah, it has to invert. It has to invert. So now for t that is less than t1, what we have is A is equal to 0. Now A is equal to 0, therefore Y should be equal to 1. Right? Now for the interval T1 and T2, what we have for this interval T1 and T2, what we have, A is equal to 1. Therefore, Y is equal to 0. For the interval T2 to T3, A is equal to 0. For this, A is equal to 0 and Y is equal to 1. For the interval T3 and T4, A is equal to 1 and Y is equal to 0. T3, A is equal to 1 and Y is low. And T4 to T5, A is low and Y is high. So this is how we can realize the action of a NOT gate. So whatever you give to the NOT gate in terms of a digital signal, what it does, it simply inverts it. It says no. It reverses its phase. It changes its phase. So for yes, it says, if we say yes, it says no. If we say no, it says yes. Now let's talk about NAND gate. And what is this NAND gate? It's a logic gate in which the output of the AND gate is given to the input of the NOT gate. And this gate is called as NAND gate. And this is basically the combination of NOT gate and AND gate. So if I have to draw its symbolic logic, it will be something like this. Let me have an AND gate, and let's assume it has two inputs, and this AND gate will be subjected to the NOT gate. And here I will have the output. So here I'll have output. And so if this is A, this is B, this is my AND gate, and here I'll get, say, for example, Y dash, that is A and B. And here what I will obtain is Y, which is Y dash bar. Okay. So the short symbolic form of NAND gate is like this. You have and then you have a small bubble on it. And this is my A, this is my B, and this is my Y, and this is my NAND gate. And if we have to write down the Boolean expression for the NAND gate, that will be Y is A and B bar. Now let's directly go with the truth table of this NAND gate. So what we have here is, let's go with the truth table. We have A, then we have B, then we have A and B, and then we have, so A, B, A dot B, and then A dot, it's A and B bar. Okay, so we can see here that we have and we better understand that how AND works. What's the logic of AND? Suppose I have 0, 0. What will be the output? That will be 0. So here I will have 1. The inversion of 0 will give me 1. So if I have 0 and 1, I'll again get 0. So the output will be 1. So if I have 1, 0, I'll again have 0. So the output will be 1. And if both are on states, 1 and 1, I will get 1. So here I'll get 0. So this will be the truth table for the NAND gate. And we can directly write down this truth table for the NAND gate in a short tabular form. And how we can write it, we can take the same thing that we have, and we have A and B, and then we have the result. Okay, so what we will have is we have A, B, and we have A and B bar. So for 0, 0, the output is 1. For 1, 0, the output is 1. For 0, 1, the output should be 1. For 1, 1, the output should be 0. So this will be the truth table of the NAND gate. The truth table of NAND gate. Now, if we try to draw this the output waveform that's obtained from this NAND gate, and try to have some waveform understanding of this NAND gate. Let me take a situation, say, okay. Okay, so this I choose as my A, and then I will have B. So B, go down. So this is my B, and so But we have the output waveform. We have to have that output waveform from A and B from the NAND gate. So this is my input A and this is my input B. So what will the output look like? The output will look like, if I divide it into some intervals, say I'll call this T1, this will become T2, this will become T3, and this will become T4. Okay, and what I will have something like this. So Y, so this is going to be 0, this is going to be maximum, this is it, and this is it. Should go like this. So T1, T2, T3, and T4. Now we can see for T, if I take T less than T1, so T less than T1, here what is A? A is 1, and what is B? B is 0. So what will be Y in this case? The Y is going to be 1. So that's why we have 1 here, okay? And for the interval T1 and T2, if I take T1 and T2, in this case, what am I have? I have A is, here is A is 0, okay? And what is B? B is 1, so Y is 1 maximum. So Y is 1. And similarly for the interval T2 and T3, T2 and T3, what I have A equal to 1 and B equal to 0. So what is the output here again? The output here again is 1. All right, and I take for the interval T3 and T4, T3 and T4, what I have, A is 0, okay, A is 0 and B is 1. A is 0, so this is A is 0 and B is 1, and B is 1 and the output is 1. So again it's maximum. So for the interval T greater than T4, so I'll say for T greater than T4, what I have A equal to 1 and B equal to 1 and Y in this case is equal to 0. Right? So this is my 0 reference here. So this is a NAND gate. Now let's proceed for the NOR gate in the similar fashion. So let me choose another video for. Now let's talk about the NOR gate. And this NOR gate, it's a logic gate in which the output of the OR gate is given to the input of the NOT gate, and this kind of gate is called as NOR gate. And the NOR gate is basically NOT OR. So let's go with the Boolean expression for NOT gate. Boolean expression for NOR gate. And what will be that? That's going to be, say, Y dash. That will be, no, let me take the Y. That's going to be Y is equal to A or B bar. This is my Boolean expression for this NOR gate. Now, if I have to go with symbolic presentation, if I have to draw it, I have OR gate, okay? I have OR. We have already discussed OR gate, and suppose it has two inputs, A and B. The output of this OR gate is subjected to the NOT gate, and here we have the output. So here, if I assume, let me take this Y, if I assume this Y dash is A or B, and this Y will be Y dash bar, that will be A or B bar. So we can have a short form of this NOR gate, and we have OR gate with a bubble on its head, and this is input A and this is input B, and here you will have the output. and this output will be y is A or B bar. Now we can easily write down its truth table now from its operation, and we can go with this diagram first. So what we have we have the truth table of this NOR gate, and I will have A, I will have B, I will have A or B, I will have A or B bar. So for OR, what we have, I'll call this A, I'll call this B, this is A or B, and this is A or B bar. So here, if I have 0, I have 1, I'll have 1, I'll have 0. 1, 0 will give me 1, will give me 0. 0, 1 will give me 1, will give me 0. 0, 0 will give me 0, will give me 1. So I can make a compact table for this NOR gate with A, B, and the final result. So I have A, B, and the output. Okay, so 0, 1 will give me 0, 1, 0 will give me 0, 0, 1 will give me 0, 0, 0 will give me 1. So this will be the final truth table for NOR gate. Now let's go with a waveform projection for this NOR gate, and what we have to have A, and okay, let's make it should be double, then let's make it like this, and okay, so this will be my A, and then I will have the B. So I will have the B, so this is A and this is B, this is T1, this is T2, this is T3, this is T4, and this is T5, and can join it like this, 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 and what will be the output? I think the output should look, if this is my zero state of Y, it will go like this. It will go like this. It will go like this. Now, here what we have is, this is my Y. So for t less than t1, what I have, A is equal to 0, B is equal to 1, therefore Y should be 0. That's there. So for t1 to t2, what I have A equal to 1, B equal to 0, so Y is equal to 0. For t2 to t3, what I have is A is equal to 1 and B is also equal to 1, and so Y here is this T2 and T3. So A is 1, B is 1, therefore Y is 0. For T3 and T4, what I have A is 0 there, you can see it, and I have B is also 0 for this. Okay, so for Y is again 0 in this waveform. So if I go with T4 and T5, for T4 and T5, what we have A is equal to 0 and B is equal to 1, so Y is equal to 0. And finally, if we go with, this is T1, T2, T3, T4, this is T5, and this is greater than T5, and this is greater than, so here T is less than T1, here T is greater than T5. So if I go with T greater than T5, what here I'll have A equal to 1, and we can see B is equal to 0. So here again Y is going to be 0. So this is how this waveform will give us the output when it is superimposed in terms of a NOR gate. Now let us see how we can develop all the primary gates, how we can construct all the primary gates like NOT gate, AND gate, and OR gate from NAND gate. So what we say here is that we can construct all of these basic gates that we have, OR gate or AND gate or NOT gate. These can be constructed from this NAND gate. Hence, this NAND gate is also called universal gate. And this NAND gate is it's considered to be the building block of the digital electronics. So this NAND gate is the building block of digital electronics. Now let's try to realize that how these NAND gates can be used as NOT gate, as AND gate, and as OR gate. So the first one we will choose here is the NOT gate. So how we build a NOT gate from NAND gate. Now for this, what we have to do is we have to give a single input to the AND gate, to the NAND gate. So we have a NAND gate and we would like to give a single input to the NAND gate and a single output. So what we have here is we have only one input and one output. And this is what is required for the NOT gate. And we can write down its truth table. So if we take it as A and B, and A is equal to B here, so Y. So what are we going to obtain here is, so we have A and we have output A. This A is equal to B. Now if I give 0, this is my NAND gate, okay? If I give 0, I'll get 1. If I give 1, I'll get 0. So this is the easiest way to demonstrate how a NAND gate can be used as NOT gate. Now in the second case that we have AND gate. We have to have AND gate from NAND. Now in this case, what we do is when the output, let me draw it, we have a NAND gate, and the output of this NAND gate is given to the input of another NAND gate. So here I have two terminals, A and B. So what happens here is that when the output of the NAND gate is given to the input of the NOT gate, so this is not here because we have only single contact here, single input. Okay, so let me keep it like this. When the resultant logic gate works, it works as an AND gate, and we can see it from the truth table. We can go with the table for this, and what we have here is we have two inputs. Say we have A and B, and then we have the output. Let me call that as Y dash, and then we have final output. Let me call that as Y. So what's going to happen here is if I give 0 with A, I give 0 with B. So the NAND output for this will be simply 1. Okay, so this output has to be subjected to this NAND gate, which has a single input. So this whole thing is acting as NOT gate. So here we'll have 0. So the next thing is going to be 0, 1. We'll get 1, and we'll get 0. So the next thing is going to be 1, 0. We'll get 1. We'll get 0. Sorry, no. So this is 0, 0, 0. We'll get 1, fine, and 0, 1. We'll get 1, fine, and 1, 0. We will get 1, and here we'll get 0. and the last will be 1 1, and for 1 1 what we get is 0, and here we will have 1. So we can see that what we have obtained the truth table of we have got the truth table of AND gate, and we can take it off, and we'll see that directly we are getting a table which is equivalent to the truth table of the AND gate. For 0 0 we'll have 0, for 0 1 we will have 0, for 1 0 we'll have 0, for 1 1 we will have 1. So this is the realization of an AND gate that we have obtained from two NAND gates, with one NAND gate having two inputs and the other NAND gate having a single input. Sorry. Now, the third one is the OR gate. And now we have to. Now let's talk about XOR gate. Now this XOR gate is also called as exclusive OR gate. Exclusive OR gate. And this gate has why we call it exclusive OR. This exclusive OR gate or XOR gate. What it does basically, it gives us high. It gives us high if either A and A or, I think, B is high, but not when both are high. When both are high. So it may be noted here that if both the inputs of XOR gate are high, then the output is going to be low. Now this XOR gate can be obtained using NOT gates. Now let's go with that. So what we have a NOT gate, and we have and we have NOT gate, and we have and so here this should be the output. This output should go, this input, sorry, should go to this, and this input should go to this, and then the output of this, and yeah, will become the input to the OR gate. So here we have OR. Okay, now let us see what I have here is NOT gate. Let me use A. So if I have used A, I'm going to get A bar here, and this is my terminal A, and this is my B, and yeah, if I give A here directly, I'm going to have A here. Okay, so here certainly I'll have B complement, and so this is my AND gate 1, this is my AND gate 2. So if I assume that the output of this is Y dash, this Y dash will be A complement dot B, and the output of this, say that is Y double dash, that will be A dot B complement. Okay, so here what we are going to have is, here we have A1 complement, and then here we will have B1 complement, where this A1 is A complement dot B, and this B1 should be A dot B complement. So so this is we can this is the original crux of this XOR gate, and we would like to write down its Boolean expression, and in short form we have a symbol for it, and that's like this. We have an OR gate, and there's a line like this, and this is my input A, and this is my B, and here I will have the output Y. So here I'm going to get output Y. Now let's write down its Boolean expression. So what will be the Boolean expression for this? The Boolean expression, yeah, that's going to be Y is A, B. Now let's go with the truth table for this XOR gate, and let's make a table first and see the output. So what we have A and we have B, and then we have the output. So this is A, this is B, and here we have the output. Now if A is 0 and B is 0, so what we are going to get here, if A is 0, we have 1 here, okay, and we have 1 here, and B is 0, so this is 1 0, okay, so here we will get 0, and and we'll get 0 here, and this 0 will be the input to the OR gate. So in the similar way, if I take now for B 0, so this is 0, so here it will become 1, here it will become 1, and A is 0, so here it is 0, so this is 1 and 0, so I'm going to get 0 here, so 0 will be the result here, so here I will have 0, and this 0 and 0 is going to give me 0. So this is how it works. So for 0 and 0, I will get 0, and in the similar way we can see that if we have 0 and 1, in this case certainly we are going to get 1, and if we have 1 0, we are going to get 1. Now if we have 1 and 1, so A is 1, okay, taking A is 1, it will become 0, okay, B is 1, 1 and 0 will become 0 here, right? So similarly here I have 1, and this is 0, 1 and 0 will give me 0, so we have 0 and 0, and 0 and 0 will give me 0. So this is what is different from that of OR. So this is our truth table for XOR gate. Truth table for exclusive OR gate. Okay. Now let's go with the logic diagram of XNOR gate. And what XNOR gate does basically, it gives the high output. So what we obtain is high output when both inputs are low. When both inputs are low, or both the inputs are high. Both the inputs are high. So let's go directly with the logic diagram of XNOR. And what we have here is we have a NOT gate, and the output of this NOT will be one of the inputs for the AND gate. Okay. So this is my A, and certainly this is going to be A complement, A bar. So here I'll take B, okay, and this B, I have a NOT gate here, and this is going to be the input for this. So this is my B, so here I'm going to have B complement, and we have another AND gate here, so as to have this is the input for this AND gate. So this is my AND gate 1, this is my AND gate 2, and from here I have B as input. So here I have input A, and here I have input B. Now the output of this AND 1 is subjected to the input, to the input of the OR gate in this case, and the output here will be subjected to the input. So here we will have Y. What Y will give us here is basically it's going to give us A dot B. So this is A and B plus A and B complement. So here we will have Y as A B complement. All right. So here we will have Y. So this is the Y. So this is our OR gate. Now, now proceeding from here, so we can have the symbol for this XNOR. So for this XNOR, the symbol is something like this. Okay, so this is the symbol for XNOR. So this is A, and this is B, and this is Y, and we can write down the Boolean expression for this XNOR gate, and then we'll directly write down its table. So what's its Boolean expression? Yes, that is Y is A. Oh shit. Y is A dot B, A and B complement. Okay. So now let's go with the truth table of this gate and and how would that look like? Let's go with the simplistic view. So we have A, we have B, and we have Y, the output. So in this case, what we have now, if I choose A0 and B0, now choosing A as 0, that will become 1 with respect to this, and this is 1, so here we have 1, and so from here we have 0, 0 and 0, so we have 0, and 0 and 1 is going to give us 1 because we have OR operation here. So for 0, 0, I'll get 1. Now let's use another combination, that is 0 and 1. So I'm choosing A as 1, sorry, A as 0 and B as 1. So if A is 0, so this is going to be 1 here, and for B it is going to be 0. 1 and 0 will give us 0, so here we have 0, and A is 0. Okay, so A is 0 and B is 1, so we have 0, and here we will have 0, and 0 and 0 is going to give us 0. So for this combination we will have 0. Similarly, 1 and 0 can be understood from the same diagram, will give us 0. And finally we have 1 and 1. Now if A is 1, this is 0 here, this is 0 here, so here is 0. So here I'm going to get 0, okay? So, and for this, here I'll have 1 and 1. So 1 and 1 will give me 1 here. So here I'll have 1. So 0 and 1 is going to give me 1. So this is your final truth table for XNOR gate. Now let's proceed with an important theorem in digital electronics, and that theorem is called as De Morgan's theorem. De Morgan's theorem. Now, what does this theorem state? What it states is that, according to this theorem, the complement of the sum of two or more Boolean variables, which are basically inputs, is equal to the product of complements of these variables. So if we have, say, variable A plus variable B, if I take their collective complement will be the complement of A and complement of B. So the statement is pure here, that the complement of the sum of the two or more, so here we have chosen only two variables, two or more Boolean variables, they are acting as inputs, that's equal to the product of the complements of these two variables. Now let us try to let's use these Boolean variables as inputs and try to prove this theorem for different cases and generalize it. Now this theorem can be proved by considering certain possibilities. Now let me choose the first possibility. Say for example A is 0 and B is 0. So what will be A complement, the summation of these Boolean variables and their complement? So that's going to be 0 plus 0 bar. So 0 plus 0 is going to give me 0 bar. So 0 complement is equal to 1. So for this case, I have got the complement of sum of these two inputs. Now let's go with the right hand side of the equation. So that is A complement dot B complement. So what we are going to get here is, so the complement of 0 dot the complement of 0. The complement of 0 is going to be 1 dot 1. So here we are getting 1. So for this case, the equation is true. Now let's use the second combination as, say, A equals 0 and B equals 1, and obtain the relation. So what's going to be A plus B complement here? That's 0 plus 1 complement, and that is simply 1 complement, and 1 complement will give me 0. And what will be A complement dot B complement for this case? That's going to be 0 complement and 1 complement. For 0 I'll get 1, for 1 I'll get 0, and their AND product will give me 0. So this is true for this pair also. So here again I can say that this A plus B complement is A complement dot B complement. Now let's use the third case. The third possibility will be A equals 1 and B equals 0. So the same story will go here, and finally we will get 0 for both the cases. And the last pair we will have here is A equal to 1 and B equal to 1. So for this case, A plus B complement is going to be it's going to be 1 plus 1 complement. That is 1 plus 1 complement will give me 1 complement, and that's going to give me 0. Now A complement dot B complement is 1 complement dot 1 complement. So the complement of 1 is 0, this is 0 dot 0, this is going to be 0. So this way we can generalize that this equation is true for all the 4 cases for if we choose 2 inputs for this logical consideration. So this is what is known as De Morgan's first theorem. This is the first theorem of De Morgan. And on the similar considerations, we will go for De Morgan's second theorem. Now, what is De Morgan's second theorem? What we have here is this theorem states that A and B complement is A complement plus B complement. So what does it mean? What does it state here is that according to this theorem, the complements of the product of 2 or more variables, we have chosen only 2 variables here, is equal to the sum of the complements of these variables. So if we would have A dot B dot C complement, that should be equal to A complement plus B complement plus C complement, and so on and so forth. Now let us test this theorem, and let's go with all the 4 possibilities here. The first possibility is for A equals 0 and B equals 0. Then A dot B complement is going to be 0 dot 0 bar. So that is 0 bar, and that's going to be 1 simply. Okay. Now A complement plus B complement. Taking the right hand side, that is 0 complement plus 0 complement. So here I'll get 1 plus 1, that's equal to 1. Okay. Now the second case is so for this case, A dot B complement is A complement plus B complement. Now, if I choose A equal to 1 and B equal to 0, what's going to happen in this case is I will have A dot B complement is 1 dot 0 complement. So this is 0 complement, so this is equal to 1. Now A complement plus B complement is going to be 1 complement plus 0 complement. So for 1 complement we have 0. For 0 complement we have 1, so we'll get 1. So here again, A dot B complement is equal to A complement plus B complement. Now third case can be understood in the same way. So A is 0 and B is 1 is going to give us the same kind of result. And finally, the fourth combination would be A1 and B1. So in that case, we will have A dot B complement. So that's going to be 1 dot 1 complement. So 1 dot 1 is going to give us 1 complement, so this is 0. Now A complement plus B complement is, for this case, so A is 1 complement plus 1 complement. It is 0 plus 0, sorry, 0 is equal to 0. So we can see that both the theorems of De Morgan hold for all the combinations of the Boolean variables A and B that have been chosen in the present context.